This is Zhaoying Bian, and I'm here to help my friend present the work in China. So, today's topic is a self-supervised non-local spectral similarity-induced material decomposition network for dual CT. And the study comes from the Southern Medical University at Guangzhou. So, here has some acknowledgements. The current PI is Jianhua Ma from South Medical University, and the funding status is about from the NSFC U21A and this U1708261. So also the other funding here. So today's topic we will present in 4 parts. First is, let me give you some background here. Okay, so for the dual CT has been used in the clinical diagnosis. So compared to the traditional, they have high energy and the low energy, and it could give some more the material decomposition and the unselected images. So in the top figures, dual CT uses these characters that different materials with different attenuation, and could provide richer image information and realizing material separation and component identification. And for example, is the, as shown in the lower right here, the dual CT can not only determine this presence or absence of stones, but also identify the composition of these calcium-enriched stones. So currently, dual CT could be have maybe 4 tabs here from different companies. It has a sequential scan, dual source, dual light detector, and ultra-fast KVP switch scanner here. So in the dual CT images have different material decomposition method. Here is the most simple image-based approach here. So the dual CT images could use this direct image-based decomposition algorithm to obtain the basis materials, and could achieve the quantitative and qualitative analysis and identify these structural components of the lesion, which has important clinical diagnosis significance. However, under this lower dose scanning protocol, the decomposition process is an ill-posed problem in this decomposition algorithm of the basis images, so which leads to serious degradation of the signal-noise ratio of the basis images. So the main reason of this noise variance is in the basis images can be expressed as this form, where this variance represents this noise, and the covariance actually represents the correlation of the noise. So it can be seen the each base, the noise in the material images has the such noise during this decomposition process. So it makes this image degraded. So currently, dual CT based image decomposition method can be classified into 2 categories. One is from the traditional decomposition method, and the other is from the deep learning based method. So in the traditional decomposition method, the model-driven, iterative decomposition method uses system modeling and the target-based image prior modeling to obtain this objective function of the dual CT material decomposition problem, and which can be optimized and solved by different optimizer algorithms, such as the ISTA, ADMM algorithm. So we can get these high quality decomposition results. However, due to this nonlinear relationship between the projection data and the base image under different energies, this method increases the difficulty of the model solving and require computing resources and face the problem of multi-parameter selection. And the deep learning method here have passed the US FDA certification recently. It makes full use of the powerful performance of the conventional neural network and use a large number of paired training data to describe the texture features and learn complex nonlinear mapping relationship in this decomposition process. So which can efficiently avoid this you pose problem and the difficulty in this parameter selections, but this method faces the challenge of being unexplainable by the deep learning models, and the high quality paired samples are difficult to obtain. So motivated by this, we consider combining the above two methods and to propose this modern data compiling-driven material decomposition method to solve the current technical limitations. So using the classical iterative soft thresholding algorithm to solve the abstract function of this decomposition model, it can be expressed as a left equation. And we can think of using the deep learning network to expand the solution to process this iterative soft thresholding algorithm, and we can get the right one. So it could be further expressed as a closed form solution. And where F here is the left inverse of F, and an iterative solution process can be represented by the set of symmetric network structures here. So therefore, this complete iterative decomposition process can be expressed as follows, and taking the high and low energy reconstruct images and this high quality basis image pair as the inputs. And each CNN module represents a one-step iterative reconstruction, and the outputs the expected high-quality base images by cascading these multiple CNN modules. And this method makes the deep learning model interpretable and can effectively solve the problem of difficult selection of parameters in comparison with the traditional iterative reconstruction algorithm. However, this performance heavily depends on the quantity and quality of the training sample pairs, and high quality basis images maybe cannot be obtained in this actual clinical process. So to avoid that problem, and this work consider this using this abundant redundant information which comes from this structure similarity and spectral correlation between the dual and the CT. So we have the high and low image, and for the block center on a certain pixel in the image to be reconstructed. With this high and low energy, we can find a block similar to it and within the corresponding range of the main image, and construct a non-local weights here. And then we use this non-local redundant information in the main image to weight the target image to obtain a prior energy image, and which we can suppress this noise while maintaining the image structure information. And finally, this prior energy image is decomposed by the direct matrix decomposition method to obtain this prior base image. So we could get a pair of this basis image here. And based on this, we construct a decomposition network guided by this non-local spectral similarity features, which consists of two parts. The first part is this iterative soft thresholding algorithm based on this decomposition network, and the other is the non-local spectral similarity feature generation. So it uses this spectral structure similarity and energy correlation of dual CT to construct a prior basis image and constrain the iterative solution process of the iterative soft thresholding algorithm, and which makes this high quality basis image unnecessary in this ISTA training process, and solve the broad problem that the high quality basis image are difficult to obtain. Oh, sorry. And so the whole loss function, we use the contains two parts. The first is the consistent loss, and the other is this non-local structure similarity decomposition loss, and the total loss is pluses with a tau as a weight factor here. And here is some experimental details. We use the clinical data from the GE discovery and obtain these virtual spectral images at 90 keV and 140 keV. So the compared methods contain this direct inversion and iterative model-based material decomposition and the supervised network, such as this CDConvNet and ISTANet. So the parameter settings are shown here. The computing source is in with this Tesla GPU here. So let me show some results with this proposed study. And here are the two material decomposition results of this study. And it can be observed that the proposed method and could produce the high quality images of this basis image and also preserve the structure information with the proposed NSSD nets here. So next, I will present some quantitatively results. So this work also calculates the PSNR and SSM and RMSE for these two basis images. So it can be observed that the proposed method can obtain the quantitative results very close to fully supervised method, such as the EastNet here. Oh, so here comes the summary. In general, this work proposed a self-supervised non-local spectral similarity induced material decomposition network, which is called the NSSD net for the dual density images. And second, this proposed method makes the deep learning model interpretable, and the training process does not require real high quality training sample pairs. And last one is we have validated the proposed method on a clinical dual density dataset and could confirm this decomposition performance of the proposed method. And thanks for your attention.
Okay, the paper's open for questions. All right, I have a couple while people are thinking about it. So first of all, so was this, you showed a ground truth, right? So are you actually using scanner data or are you generating scanner data from that ground truth?
So from my understanding, because it's not my paper, so from my understanding, and it comes from the clinical data. Yeah, because it has dual density images and use this process to generate this prior image with weights, with the mean value and the non-local weights for these noise properties, and to generate the paired low and high energy inputs and the related direct decomposed images as their target. So they treat network here.
Let's see.
Yeah.
All right.
Thank you for the nice talk. There's also the fast version of ISTA, the FISTA algorithm that includes the Nesterov momentum. And I was wondering, is it possible to include this momentum into the design of the network to achieve like an improved like convergence, which would mean a reduced size of the network?
Oh, yeah, that's a good question. And I will keep this point to the corresponding author. Yeah, because I didn't have this implementation details for this network. So, but that's a good suggestion here.
Okay,
I will
thanks.
keep your points to the, thank you.
Okay, I have one more question about the endpoint here. So you're showing results for the water bone decomposition, right?
Mm-hmm.
But are you planning on showing these images, or what do you see as the image that you're gonna, I mean, most of the time when people do dual energy, they show like a virtual monochromatic image. You know, they combine them, the basis.
Yeah, so I believe if you have this water and bone, you can generate different monoelectric images, right?
Right, but then the interesting thing would be then like, how do all these different methods compare on that final image that you're going to show?
Oh, you mean at different energies, if you, but the noise properties here should be the same if I understand correctly, right? So if you got the basis materials, it is energy independent. So the noise properties is a linear process if you want to generate different
Sure. Yeah, you
images.
can do that. But like if you go to the next slide, for example,
yeah,
you're reporting like a PSNR, SSIM, and RMSE based on the basis images. But if you combine the bone and water to make your virtual monochromatic, you can also then have those same metrics, but on the virtual monochromatic. And I was just wondering if the trend would be different, or maybe the differences wouldn't be as much, or if the differences would remain.
Oh, that's a good question. And from my understanding, I believe it should be the same.
Okay.
Yeah, it depends on which region you choose, right? And which part you want to calculate for this quantitative comparison.
All right. Okay, thank you.
Thank you.
Any other questions? Okay, if not, let's thank the speaker again.